Okay, so this week's problem 4 was called height 1. And basically, it's a fairly standard problem where you're trying to find the position of the closest smaller element to the left. And if there is no such element, you report it as 0. So I'm going to start off with this example where we have 5 buildings and the numbers are the heights of the buildings. And then since n can be up to 2 times 200,000, you either have to do an n log n solution or O of n solution. And we can do this in O of n time, which is the solution I'll be showing. So in order to do this, we'll have to use a stack. And I'll just represent the stack at the bottom right here. So I'll just go to the example because it's easier to explain that way. So first, we look at this building. And then at first our stack is empty, obviously, because we haven't processed any nodes, any buildings. And then we look at this, and then since our stack is empty, like we know that there's no buildings that are smaller than it before to its left. So that means we just report 0 as the answer. So the answer to this would just be 0. And then after that, we would add 3 to the stack. And the stack is going this way. So the elements to the right are at the top of the stack and at the bottom at the left. So then we go to 4. And then we can see that the top element is 3. And for each of these for each of the things we add to the stack, we'll also we'll create a pair and like also add their position to the stack. So we'll know that the position before, the closest position before that was smaller is 1. And then we add 4 to the stack. And then we process this this tower in this building, and then we see it's 2. And in this scenario, we see that like for future elements, whenever you're searching for the nearest smaller one, since this building is always smaller than these two, you know that you'll never have to like look at these again because these will never be the nearest smallest element again, because this is both nearer and smaller to all the remaining elements. So so then we can just eliminate these 2 from the stack and then just insert 2. Oh yeah, before that you look and then you see that there's no elements in the stack that are smaller values. So then you just report it as 0. And then you insert this and you can eliminate these. And then you move on. And for 5, you look, this 2, you can report it as position 1, 2, 3, 3. And then you insert it onto the stack. Position 1, you see there's no smaller, and then you report as 0 because there's no smaller. And then you eliminate these to insert 1. And then you see that there's no elements left and your algorithm is complete. So basically what you can see from this example is that the stack will always be monotonic. It will always be increasing from bottom to top. And basically, in order to like, when you add an element in general, you just look at the top of the stack in order to find the nearest smaller element. And whenever you're trying to insert an element after you're done like looking at the stack, you'll eliminate all elements. You keep eliminating elements at the top that are smaller than the current element you're considering. For instance, at one point we had 3, 4 in the stack. So because when you're considering future crease, the 2 is nearer and smaller to all these elements, so you don't need these elements anymore. So the algorithm for inserting is just to keep on looking at the top of the stack. If there are elements, you just eliminate, you keep eliminating the top element until the element is until the top element is like less than or equal to the current element you're considering. In this case, none of them are less than or equal, so it just becomes empty, and then you insert it. And like if you look at a couple more examples, you'll definitely be convinced that the top element will always be the nearest and smallest to whatever element you're trying to process. And it's a pretty useful trick to like not have to check if the stack is empty all the time and like avoid errors. For this problem, it says that you should report 0 if there is no such position that is smaller. So we can create an imaginary like building with height 0, so that like the stack starts off. Okay, this will be our new stack. This will be the direction. So it'll start off with 0, and then now when we go to 3, well, this 0 will be the answer for this 3, and then we'll insert it. We'll insert 4. 2, we'll check the top one is 4 is greater, so we eliminate it, and then we check the top one again is 3, it's greater than 2, we eliminate it. But this 0 is smaller than all of the elements in the array because the values of the heights are from 1 to 10 to the 9. So you know that like you'll never eliminate this 0 because it's always smaller, and it's always less than or equal to all of these elements. And then you just insert it. So you never have to worry about like having an empty stack. And then you have 5, and then you have 1, and then you look at 5 is greater than 1, eliminate it. 2 is greater than 1, eliminate it. But 0 is not, and then you just insert it. Okay, I'm going to implement it now. Okay. So this is obviously just reading in the input. Since I'm too lazy to create a custom class that has 2 members, I'll do import javafx.util.pair, and this imports a class, a generic class that you can use to basically store 2 elements at a time. I'll just use it, and it should become pretty obvious. Like this type of pair stores 2 integers, which you can specify inside of the template, the parameters, and yeah, it just makes it's just a lot easier than creating your own custom class again. And I'll be using an array list for a stack this time, because I always forget the methods for a stack. And using an array list for a stack is basically the same thing. I'll continue reading in input. wait, just not that. Okay. And to create a new pair, you just do new pair and then put the two values you want to store, and these two values have to correspond to the types up here. So this is the actual algorithm. We loop through all the elements from left to right. At the beginning, we add a pair. Okay, the first value, the element to the left is storing the actual value of the element. And then the element to the right is storing the position of the element that we will report. So this was the like imaginary node we have. It's at position 0 and its value is 0. And then now we're considering node A, and we look at the top of the stack and look at the get key returns the first element, so which is the value. So if the value at the top of the stack is greater than or equal to the current element, then you just remove it, because you know it'll never be the answer, because the current element is both nearer and smaller to all the remaining elements to the right. So you can just remove it while this is true. And then when this is done, you know that there will be the next element at the top of the stack will be smaller than the current element, and it'll be the nearest one. So you can just simply print that out as the answer for this this position. Get value gets the second value, and which in this case is the position of the element. And then we add to the stack our current element. And remember, we need to make this one indexed because that's how the problem is. And then I like to print out new line at the end. Okay, I think this is right. Oh yeah, I forgot to throw IO. All right. Okay, this was right. Are there any questions?